Okay, so welcome everyone to HEC Montréal's Chair in Energy Sector webinar series. Today we will present you one of our latest report, which looked at decarbonization of long-haul trucking in Eastern Canada, specifically looking at the simulation of e-highway technology on the highway corridor between Quebec City and Windsor up to the US border. This project was done in collaboration with CPCS and Clara Kaiserbril is the main author of the report that we did, and she did all of the simulation. She's a global director of power at CPCS. And I know many people know already the chair a little bit, especially with the work we're doing with Pierre-Olivier Pinault, and mostly stuff that is, I would say, focused on energy systems in Quebec. But I will let, just briefly before we start the presentation, Clara just give an overview of her consulting group so you can better know where they're coming from. So Clara.
Hi everyone. So CPCS is a management consulting firm. We are headquartered in Ottawa with offices throughout Canada and the US, as well as in Africa. We have a lot of international operations in Africa. We specialize in the power and transportation infrastructure with a strong focus on private participation in infrastructure development. And in Canada, we advise various public and private organizations on the development of their transportation infrastructure, be it by road, by rail, or on the sea. Back to you, Joanne, for the presentation.
So I'm not sure I even presented myself, but Joanne Whitmore, I'm a senior researcher at the CER. So, anyways, just before maybe we start more officially, normally I think everyone is on mute right now. For the question period, you can write your questions in the Q&R section. It's the first time that I'm actually using the webinar Zoom platform. So I would hope that perhaps if you lift your hand, there's like a little button for that. I'll try to see if I can give you the possibility to mention your questions live. Otherwise, unfortunately, we'll have to read it out and then answer it as much as we can. So the presentation will be 40 minutes long, maybe a little bit shorter, and then the rest of the time is going to be to have a discussion with the people. Just before we start, just want to make clear that this is not an endorsement of a technology, even though we're looking at one technology in particular. Just how this study started is because with a lot of the work that we have been doing in Quebec, we noticed that especially for freight transportation, which is extremely complex, a lot of the decisions that are being made by government and other decision makers are often done in a very isolated way, where we just look at technology and some people have preferences and stuff like that. But there wasn't a comprehensive study that was looking through a more sort of systematic approach and methodology to compare different studies. So this is why we reached out to CPCS and we want to try to see how eventually we could do a larger study to have a more objective way of looking at, and in this case, large trucking, long distance trucking freight in Quebec and Ontario, because of course you can't just limit long distance freight to one territory, given that they are always moving. And so this was like the beginning to see if we can do something based like that, really looking at a segment that we know between Quebec and Windsor, where there's the most concentration of class 8 and superior freight. So just to put that into perspective. So the presentation, we're going to just have a quick overview of our study and present the e-highway concept, look at the model, the methodology that we used, some of the key assumptions, results, and obviously some of the conclusions. Clara, if you can go to the next slide, please. So as many of you know, of course, freight transportation is one of the most challenging sector to decarbonize. It's, I think, why a lot of people in the university have a hard time to really deal with this. It's so complex when you start looking at the logistic chain, the regulation, the cross-border traffic. It can become a very overwhelming when you compare, for instance, personal transportation. But it's still one of the most GHG intensive sector. In Canada, it represents 8% of our national emission, which has tripled since 1990. What makes it also very challenging is that it supports our daily economies and activities. And as we saw during the pandemic, increasingly important to have e-commerce and just in time and stuff like that. So it's really become entrenched in our everyday life. So, but still, to achieve our net zero emissions by 2050 is going to require decisive action in that sector, technologically wise, but also logistically wise. And the current initiatives that we looked at the federal level in Canada, what you can see in the report is actually quite insufficient to place Canada on a clear path towards zero emission freights in the time frame that we've set out. Of course, we have the carbon tax that's going to ramp up to $170 by 2030, but we also have some measures for improving standards on heavy-duty trucks, also subsidizing alternative truck technology and fuel, and we're going to have soon the clean fuel standards for regulating minimum levels of biofuels. But even when we look at that, it's still not sufficient. So we need to start really looking more in depth. Also, the reason why we did specifically this current study on e-highways is because some of the limits of current approaches has led us to think, well, why not e-highways? I mean, we're looking at hydrogen, we're looking at batteries, and we're looking at other alternative fuels which are not fully decarbonized. But when we think of natural gas, for instance, and eventually biofuels and so on, so they all have some potential, but also a lot of challenges. And I think that's why we said, well, why not look at this technology, which we'll see later on why it could have a potential. But essentially, e-highways is an overhead catenary system that directly powers heavy truck engines equipped with pantograph on a dedicated highway corridor. There's different types of e-highways. You can also have some that is by induction, which is connected by sort of underneath the truck, but we didn't look at this. We specifically looked at the catenary because that's the one that is mostly being piloted and tested right now in other jurisdictions. Next slide, please. So the objective of this study specifically was to simulate the potential of e-highway technology for decarbonizing freight transport on a 1,300-kilometer segment of the l'autoroute 20 in Quebec, which becomes Highway 401 in Ontario, and it connects basically Quebec, Montreal through Toronto up to the US border. So this is basically where there's some of the heaviest flux, if you want, of class 8 and above truck. And so this was the interest of limiting the work to that segment. And we did this based on the GIS analysis of current flows of heavy vehicles. And it's based also on the road capacity of that highway. And this is all work that CPCS really could master, and they did within their firm. The study, specifically in this case, we considered hybrid diesel catenary electric trucks because it can actually be full battery or it can run on other forms of hybrid fuels. But the hybrid diesel model is the one that's already being used for testing. So we started up with that to see what would be the potential. And it's also a study which, like I mentioned earlier, is part of a larger, broader study that we want to do, because the point is not to pick and choose a technology, it's really to better understand what are the limits, the benefits, or the constraints for a specific geographical context and usage in a region. So just quickly, the e-highway is basically a concept which seems new, but it's actually based on old technology. I mean, we can obviously all know about trolley trucks or trains that have pantographs. So we're basically just doing a transfer of that technological concept to large freight trucks. It's basically a supportive structure that's built outside of road boundary, and it holds on two overhead catenary, which supplies a positive and negative electric circuit, as you can see in the photograph that is based on a real model, obviously, in Europe. The electricity is transferred to the truck through the pantograph, and then a secondary source of energy is used outside to electrify the road. So the other source can be diesel, or it can be long battery, or eventually other forms of fuels. But the thing is that the pantograph on top will basically come back in when you have to divert to do your last kilometers of delivery, and then when you get back on the highway, then you bring it back up automatically, and it connects to that grid. And the technology is flexible in the sense that the trucks are can continue, are able to circulate on any road type, whether or not it has the catenary system, but it doesn't also prevent other types of vehicle to be able to be on the same roadway. So next. So the relevance for the Canadian context was basically because in Canada, we have a pretty linear transportation network compared, let's say, maybe to Switzerland, where it's not so linear, even though they do some pretty amazing things with trains. Here, we have a pretty straightforward main arteries for our corridors for transporting long distance goods. It's also, we have a lot of clean and affordable electricity, especially when we think in Quebec, where we have surplus of electricity, cheap electricity, which is already quite an advantage compared to Europe, which is considering this technology. And also, well, of course, you can use the existing road infrastructure that in Canada tends to be pretty actually wide. If you think of the Autoroute 20 and the Highway 401, so that's there's adaptability that can be done. It's also flexible, like as I was saying, that even though you can start up with a hybrid system, which will be less costly, eventually you can move on to other truck systems such as the ones with battery over time. So the infrastructure remains relevant even as you change trucks. And then there's been some tests already with the pilot projects in Sweden, because of course, if we have an ice storm, it's quite important that it can go through that condition. Just more generally, some of the relevance is also that it's a known technology. So actually a lot of the patents for the catenary are available since the technology has been there for over 100 years. It's more for the trucks, of course, that there's more some proprietary stuff, but still, I mean, it's a known technology. The efficiency of using directly the electricity can be quite interesting, especially if we want to have a diverse usage of this clean electricity. I mean, we have to not forget that it's, we're going to want to use clean electricity for heating, for our industries and so on. So there's going to be increasingly a competition between electricity, clean electricity as we move forward in time. And so this is one of the most optimal way to use clean electricity in transportation. There's also no downtime for recharging battery in the event that you would have a truck that would be 100% electric with batteries, then you can already be charging it as you're driving on the highway. And then there's also lower maintenance and repair costs in certain zero net emission technologies. And of course, there's a potential for significant GHG reductions. So this is just to show quickly like that the efficiency varies between technologies, and it's extremely important, given that it will determine how much overall energy we need to support this freight system. And so, you can see from power to gas to hydrogen, where the efficiency is between 20–29%. And as we go up for battery, it can go up to 62%. But the electric road system is for now, one of its biggest advantage is really its well-to-wheel efficiency, which for this analysis was 77%. So there is that, which is considerable. The next slide, please. So this is just to give you some of the pilot tested projects that are already undergoing. So in Sweden, which was one of the first country to try it out. In 2016, they have, with the Scania company, a 2-kilometer highway that has been electrified with that technology. There's Germany that's been having also ongoing projects with 10 kilometers already near Frankfurt, and there's another segment of 5 kilometers near Lübeck. And then in California, we have a pilot project, which is near the port, where they do often back and forth of delivery, and they have a 1.6 kilometer track there. But there's still a lot of other, based on these pilot projects, certain governments that have decided to look at the possibility of, like Sweden, to bring up to 2,000 kilometers of ERS by 2030. And this wouldn't just be the e-highways, they're also looking at other types of ERS, but still 2,000 kilometers, that's quite significant. There's also Germany, which the government has considered, based on the success of the pilot projects, to perhaps go up to 4,000 kilometers for their highways. And then there's Italy, France, and the UK, which are also considering some of these options. So sorry, this was my part. And now for the more technical part, so the results of our simulation. Well, first of all, more what we included as hypothesis, and then the result is Clara. Thank you.
Many thanks, Joanne. So now let's take a deeper dive at what we have done considering e-highway technology for Eastern Canada. So as you can see on this map, we have really based our study on real life data on truck traffic, starting from Rivière-du-Loup up north, all the way to the US-Canada border in Windsor. What you see on this map is real life long haul heavy truck traffic that we have just taken from publicly available data from the Ministries of Transportation of Quebec and Ontario. And we made a number of assumptions to derive from this publicly available data just the larger trucks, so class 8 and above, on long haul trips, because the e-highway technology is mostly relevant for that category of truck, and for long distance trips. For shorter distance trips, there are other options that may be more relevant. So really we have focused on trucks that do long distance along this corridor. The overall length of the corridor is slightly more than 1,300 kilometers, and we have divided it in several segments. We have also omitted the major cities because it's less relevant for those areas. First, the cost of deploying the technology would be much higher, because when you are closer to the cities, you have more roads, more bridges, flyovers, etc. That will make it much more complex to build the e-highway. You also have less space to build it, so you would have like right-of-way issues. And also a lot of long distance transportation use logistic hubs that are outside of the main cities. So this is why you can see the area around Toronto and Montreal is not covered in our simulation. Our model is relatively straightforward. It's an Excel-based model that considers the techno-economic parameters of the e-highway, and I'll tell you more about that in a second. And also uses scenarios for the deployment and the adoption by the industry of this technology. And as we will see, adoption by the industry is a big question mark and is a key parameter to determine whether the technology makes sense or not. What we get from this simulator is first the cost, so the overall investment cost, the operation and maintenance cost, and of course the cost of electricity to power the trucks. And in terms of benefits, we have considered two benefit streams. The first one is avoided cost of fuel, and the second one is avoided CO2. The way the simulator works is we consider a baseline where all the traffic remains diesel-based as it is today. And we compare this baseline business as usual with the e-highway technology. As Joanna mentioned, this simulator was developed not only to test the e-highway technology, but also to compare it with several other technologies. This would be a larger study that we hope to be able to conduct soon. So really what we want to do is to use one simulation to compare several technologies on a given real life segment between Quebec and the US border. So in terms of techno-economic parameters, we have had a look at the literature. Maybe an important thing to mention is that e-highway today is mostly sponsored by one large industrial group, that is Siemens in Germany. So a lot of information that we have on the technology come from Siemens, and we have consulted with them throughout our study to make sure that we got the experts tell us about their technology, but we have also looked at a broader range of literature to make sure that we do not obtain all our information from one single source, which would be biased. So we looked at the infrastructure costs that we could find in the literature. We noted that it ranged from approximately 2.5 to almost 5 million Canadian dollars per kilometer of infrastructure. We have selected something in the middle, not because it's in the middle, but because the higher costs correspond to very heavy traffic, because the heavier the traffic, the more power you need to inject in your catenary system. So the more substations you need, the more expensive it is. So this higher cost was too much for the traffic that we have here on the highway segment that we have considered. Hence our choice of this assumption of 3.6 million per kilometer of installed infrastructure. And then in terms of electricity consumption, we took the median number from the literature, that is 1.5 kilowatt hour per kilometer. In terms of assumptions, we have also used assumptions for the extra cost per individual truck, because you have to add a pantograph to a regular truck. We followed the literature in assuming that the cost would decrease as the technology is more widely adopted. So from approximately 70,000 per truck today to 20,000 in 2040. In terms of diesel consumption, carbon contents of electricity, carbon contents of diesel, we just used statistics representative of Eastern Canada. And as you can see, as Joanne was mentioning, in Quebec, we are blessed with extremely clean electricity and quite cheap as well. But Ontario also has a very good clean electricity mix with only 40 grams of CO2 per kilowatt hour. We have included in our model the value of avoided CO2 to put a number on that value. We have used the federal carbon pricing policy. So we have aligned with the numbers that they have published, that is slowly increasing from $30 per ton today to $170 in 2030. One important thing also to mention about the simulation that we have conducted is that we have conducted it from the perspective of the entire community. We don't do it from the perspective, for instance, of one truck entrepreneur who's wondering how much they will have to pay for the trucks and how much they will gain in terms of savings on fuel. We have considered the entire community, so both the trucking industry and the government that may be paying, or the society at large that may be paying for the infrastructure. And we have not tried to decide which stakeholder would get what fraction of the benefit. So it's really an economic analysis looking at the community as a whole, and not at the benefits for one single user of the technology. So we have used our simulator to conduct several tests. We will present three tests here. The first one was to check the, let's say, the most favorable scenario. Imagine that you built the infrastructure overnight, and that overnight all the trucking industry starts using e-highway. So under this, let's say, theoretical optimum, but not achievable in real life, we see that the simple payback period, is relatively short for an infrastructure that size. So the simple payback period is the period of time after which all your costs have been paid back by benefits. So in our case, avoided diesel cost and avoided greenhouse gas emissions. And in less than 10 years, 7 years for the segment with the densest traffic, and 12 years for the segment with the lowest traffic, we can fully repay the initial investment cost, both in terms of the cost of infrastructure and cost of fitting trucks with pantographs. But this, of course, gives us like the most favorable case. And now we wanted to look at a more realistic scenario of progressive deployment. So that's our second test. We consider that the first segment to be electrified will be between Toronto and Ottawa in 2025. Then we continue north east to Montreal and southwest to the US border. And then we electrify the northern segment north of Montreal up to Rivière-du-Loup in 2040. So this is a more progressive deployment that is more realistic, both in terms of adoption by the industry and the time needed also to build infrastructure. So this shows our deployment scenario in terms of adoption by the industry. We assume that at the beginning, so when the first segment is built, we have just a few hundred trucks that switch to the technology. And then as time passes, more and more trucks switch to the technology. So at the beginning, we have just a few hundred, and that represents 0.2% of the combined heavy truck fleet of Ontario and Quebec. So we consider that this is a realistic assumption. And then slowly it progresses up to several dozen thousand of trucks that represent at the end of our simulation horizon, approximately 13% of the combined Quebec and Ontario truck fleet. So the results that we get under this progressive, more realistic scenario is an economic range of return between 7 and 10%. 10% is for the segment with the highest traffic, and 7% is for the entire range. So the economic rate of return is a way of expressing the total benefits as a percentage of the initial investment, and it's very similar to a discount rate or to an interest rate on a mortgage, for instance. So it's really the same kind of metrics as an interest rate. And 7% for an infrastructure that size is really reasonable. This 7% corresponds to the benefits that we make, so 2.8 million ton of CO2 avoided every year, and oops, sorry, this is still in French, 360 million Canadian dollars of avoided fuel costs. And we compare that with our initial investment in the infrastructure, that's 4.1 billion, and 0.7 billion of extra costs for the trucks. So we realized that with this relatively realistic scenario, we arrive at an economic rate of return, so a metrics of the economic viability of the technology that is quite acceptable. Another important test that we run was to check the sensitivity of our results, because even if the technology today is pilot tested, as we have seen in several countries, it is still not a commercialized technology. We do not have large scale deployment of the technology, so there's still some uncertainty on the cost and of course the benefits. So we run our simulation again, and making one parameter vary at each time. And we found that the most sensitive was to the cost of diesel, because it's our baseline. If diesel is more expensive, it means that you save much more by switching to electricity. So the cost of diesel is one important parameter, and if it increases in the future, it will make the technology much more attractive. The second most important parameter is the rate of adoption by the industry. And that is, of course, just like every large infrastructure with important upfront cost. If people do not use it, you have lost your investment. And that's a super important question mark. We cannot rely on international experience so far to answer that question, because first, as we said, it's being pilot tested, but not yet commercially deployed. So we do not have real life data to tell us more about adoption by the industry. And there's also the fact that even if it was widely adopted in Germany, we need to understand what is specific in Eastern Canada that would make the industry more prone to adopting the technology or less than in other jurisdictions. Then obviously the cost of infrastructure is another important parameter. In terms of sensitivity, we are a little bit more comfortable there because, as Jean was mentioning, overhead lines for catenary system is not a novelty, so the costs are relatively well known, and it exists also in Canada. So we consider that we have less unknowns about the cost of infrastructure. And then it's less sensitive to the cost of electricity, the operation and maintenance cost, and the cost of putting the pantograph on the truck. That's a relatively less important parameter in terms of viability for the technology, but it's probably going to be a super important parameter from the perspective of each individual truck operator when deciding whether they want to invest in the technology or not. So the conclusion of this initial simulation is that at first sight, it is an interesting technology. And as we were mentioning earlier, decarbonization of heavy freight is a real challenge. What we have on the table today may not be sufficient to achieve Canada's goals in terms of GHG reduction. So based on our initial simulation, we feel that e-highway should probably be considered among the other options that exist, because it pays back in a minimum of 7 years under extremely favorable conditions, but still it's a good indicator. And with a more realistic scenario, we have economic rate of returns of 7 to 10%, which is also quite a good metrics. We made a quick calculation. It was not part of our simulator, but we made a quick calculation of the cost per ton of avoided, the cost per avoided ton of CO2, and we arrive at numbers ranging from $65 per ton under super optimistic assumptions to a more reasonable $200 per ton, which again is relatively reasonable for abatement cost. Many questions, though, remain open on this technology, and the first and most important ones regard the perception of the trucking industry on the technology, whether it's compatible with operational constraints, whether it's compatible with the way they want to operate. We had an interesting comment also when presenting this study during another webinar on how do we handle the border with the US, and the fact that most trucks do not stop at the US border, but they continue. So it would make sense to have a coordinated approach with the US as well. So there are all questions related to the operations, how it would actually work. Another important question that we have not addressed here is what would be the optimal financing structure, because we have looked at the cost of building it, but there will be also costs for financing it, and there will be decisions to be made regarding the allocation of benefits. If you can save a lot on diesel cost, who gets to save, and how much would, for instance, truck operators have to pay to be allowed to use the technology? What would be the tariff of electricity for e-highways, etc. So how do you finance it, and how the costs and benefits are allocated between the stakeholders is another important question that needs to be answered. The technical feasibility also needs further investigations. As we said, it's being pilot tested in Sweden, but Sweden has a cold climate, but ice storms that are relatively frequent here are not really a thing in Europe. So one super important question is whether it can actually withstand an ice storm. Initial discussions with Siemens experts tend to lead to the conclusion that it can probably with just minor reinforcements, but that's an important question. What about clearances too, when you have to go under a bridge? How does that work? Will it increase the cost? And then one last important question is about how the electric highway is used. What we have considered in this simulation is the full electrification of the highway with hybrid trucks that run on electricity when they are on the highway, and on a secondary drivetrain with a secondary fuel when they are outside of the highway, whether diesel, biofuel, LNG, and they only have a small battery with a short autonomy to for instance, when they are taking over or moving lane on the highway. But another probably very interesting option that could be envisaged and simulated is, instead of electrifying the entire highway, only electrify smaller sections for on-the-go recharge of 100% electric trucks. So instead of running on electricity from the catenary system, it would be electric trucks that use the catenary system only for recharge. That's an interesting option. To our knowledge, it's not yet pilot tested, but it may be a way of getting the best of both worlds, both the electric trucks that is a growing market, and using the catenary to save the time for battery charging. As a last point, we really would like to have the opportunity to compare this e-highway technology with a long list of other technology. We would like to apply the same methodology using this highway corridor in Quebec and Ontario to simulate various technologies for decarbonization and be able to compare them to inform policy choices. And we would like to look not only at their carbon footprint and economic benefits, but also the technology maturity, the difference in terms of capital investment requirement, how much does it cost to build the trucks, what's the feasibility in the Canadian context, because a lot of these technologies exist elsewhere, but what about here in Canada? What do stakeholders think? What are also the options in terms of intermodality, complement with rail and sea transportation, interjurisdictional issues, etc. So this is our ambition to expand our study to compare several technologies with the e-highway. Thank you very much for your attention. Joanne, back to you for the discussion.
Maybe if you can also go to the next slide. So for those who are interested to download the report, and also this webinar is going to be on our HEC YouTube channel, so you can see it again. and the PowerPoint will also be available on the webpage on our HSC. And if you have specific technical questions about the trucks and the technology, unfortunately, this is not so much our expertise. We invite you to talk to Patrick Ackerman, because he's the one that we have been able to contact when we had questions, more technical questions. So hopefully you can get some info there. But otherwise, I'll just take quickly some of the questions that some of the people have answered, have sent. So Clara, maybe you can come back in. And just a reminder that the point, we're not trying to look at only this technology and say this is the technology, because we want to be able to look at hydrogen, like battery, and they all have issues. I mean, all of them are going to have issues once they get to the border and go to the US. It's going to be the same thing with hydrogen. It's going to be, so I mean, it's to look at what are the opportunities if they have that challenges to overcome them. That's something. What are the likelihoods that we can get over some of the regulatory issues or the manufacturing issues, which is such a key fundamental point when we talk about freight transportation, because everybody wants to put a technology forward, but this is something we have to plan out, and the first step is to do this study. That it's just to look at it in an objective way, comparing the same parameters for all of them, and see what we can do where we have more flexibility, and perhaps have a sort of hybrid approach where there's no one silver bullet to replace diesel, but maybe we're going to have to do something progressive over 5, 10, 20 years, and that's the reality of the thing to decarbonize. So quickly, the first, somebody had asked whether the study, it says, I assume we haven't studied this technology before because it would not make economic sense to develop the infrastructure if we weren't in an energy transition context. Well, that's like, I would argue, most of the technologies, even hydrogen, even LNG, there's all kinds of different challenges. And of course, what's precipitating us to look at these options is because we have a climate imperative that's imperiling our economies, our societies. And so we have to look at different options to move goods and to have our daily economic activities. But yeah, I mean, none is perfect at this point, not just this e-highway. I think all of them, but maybe Clara, you have some better insights.
No, but it's true. I mean, one of the reasons why people are looking at decarbonization technologies because we need to decarbonize. This being said, we have also simulated the technology without accounting for the benefits of decarbonization. So, in other words, setting the value of carbon to zero. And what we found is that the payback period would be something like 20 years. So you still save on the cost of diesel because electricity is cheaper in terms of energy contents, but it takes much more time to recoup your initial investment. So yeah, it could make sense even if we weren't trying to decarbonize, but the break-even point would be a bit more elusive.
Somebody else asks about the Canadian weather, because it, of course, can fluctuate more than Sweden, especially if we're looking at the possibility of applying this technology across Canada. But yes, I mean, that is a challenge. I mean, that there is some study, I guess, that's been done for trolleys and trains that run with catenary. We do have some in Toronto and stuff like that. But yes, there's definitely more work that needs to be done on that specific issue, and I think it's also the same for other technologies. But Clara, because you've worked specifically on that technology for train, maybe you have insights.
No, I don't have much more to add. I mean, as you say, Canada has some experience with catenaries, but it's not as widespread as it is in Europe. And we have some partial answers because the technology is being tested in Northern Europe. But yes, definitely more studies are required to make sure that it would work with Canada's extreme climate conditions.
Yeah, and for that, I think if you contact perhaps Patrick Akerman, because obviously he's closer to the pilot projects that have been done in Germany and Sweden. And so they might have some analysis on some of the issues, like, again, it's Sweden, but I mean, it can give some insight for those that want some more technical results and data. Other question is how current industrial players receive those propositions. Are they open to such transition? Well, I mean, we did have a presentation. We presented this to the Fédération de la Chambre de Commerce du Québec, which is grouping many industries, some of which are part of the transportation sector for freight. I think, in Canada, it's relatively new. There hasn't been a lot of prospective analysis of the application of this technology. So everything's to be done. And I mean, we're kind of hoping that this first study will initiate, like, we're just planting a seed, and everybody that can bring up some new studies using this as a basis to further it, then great, but yeah, I mean, there's a lot of questions to be answered, just as all the other technologies, and so I think everybody tends to be a bit more conservative and skeptical until there's more like proof and data that's available. Clara, I don't know if you have that same sense.
Yeah, totally. We really wish to have the opportunity to do this wider study and do more consultations with the industry, because it's a key parameter to decide if the technology makes sense.
Yeah, and I mean, that's the whole point. The larger study we would like to have some very diverse working committee to help us to refine and validate some of the hypotheses that we're going to be using in our simulation, because that's the only way that we can advance and make it as transparent as possible, because a lot of stuff has been done perhaps for the government, but we never get to see the data. So the point here is to really bring this out. So you bring the hydrogen guys, the Lion trucks, you bring the operator and manufacturers, and we have this frank discussion so that we have the best information for the simulations that we do. That's what we're hoping for. So somebody else asked, what needs to be done in Quebec in order to move the topic forward? Well, I don't know. I think this is a first start. We need to just start studying it in an objective way and see how it compares to, Quebec is already investing massively in hydrogen and looking, of course, at battery options and so on. And we haven't even started to look at logistics optimization options, but we have to just do more transparent and collaborative work as this, so it can start being perhaps considered. Clara, do you have more stuff that you guys are doing at CPCS that you can
not specifically in Quebec, but one thing that's obvious is that a lot of the work we do right now for especially for governments in Canada and in the US revolve around decarbonization options, including not only on the road but also seaways in Eastern Canada.
Right. So somebody else asked, is the motors trucks fabrication industry working hard in the more efficient process to fulfill the demand of the project? Not quite exactly sure how to take that angle. Maybe Clara.
Well, right now the pilots that exist have been co-developed by Siemens and Scania. So I think Scania is from Sweden. So to our knowledge, Scania are the ones working on the development of the technology, while other truck manufacturers are moving towards 100% electric or hybrids. So right now, there's one manufacturer that we know is actively developing this technology. I imagine that there will be others if the pilots in Europe are successful.
And I think that actually for the California pilot, it's I don't want to say, but I think it's that's Mercedes. I'm not sure. We have to double check, but it's not Scania. So there are some other companies looking at that. Somebody just made a comment to say that in India, they're already planning to build 1,300 kilometers along Delhi to Mumbai of e-highway. So there you go. There's other countries which are considering that. we haven't had the chance to look into that.
Yeah, I just checked it as we were talking. Okay. It's super interesting. Thanks for bringing it to our attention. Yeah. We had tried to do a worldwide review of what's going on, but we had missed that one. So if someone else knows of other projects being developed or considered in other parts of the world, I don't know, for instance, what China is doing. It's a big blind spot in our study. Maybe they're also looking at the technology. So if you have information, we're glad to learn. Thanks.
So somebody says, in addition to the technical and economic costs, did you consider taking into account the environmental costs of creating the infrastructure for e-highways? So, Clara.
So no, we didn't. I would say that at first sight, the environmental cost is probably relatively small as compared with the benefits, because we are not, for instance, we are not using more land. The infrastructure itself can be built mostly on the side of the road. So sorry, my English fails me, mais sur l'accotement de la route, on n'a pas besoin de dégager beaucoup plus de terrain, donc il n'y a pas de question de changement d'usage des terrains. And switching back to English, I think in terms of gray energy, so the environmental footprint of building, sorry, of the construction materials, it will also be relatively limited, because except for the small buffer battery in the truck, that has, as we know, batteries have a relatively large environmental footprint. But apart from that, it is mostly steel that, I mean, is not eco-friendly, but is not known for a heavy environmental footprint. So I tend to think, but it of course requires more studies, that the environmental cost of building the infrastructure is probably small as compared with the benefits. But again, it's a very good point, and we could try to have a closer look at that in the future. Thanks.
Somebody asks, are the costs of infrastructure based on what we know today of catenary pantographs, or it's a factor in it, or it factors in reduction of price with scaling up of the technology worldwide? Clara, I think you would be better positioned.
Yeah, so we have considered likely reduction of cost for the pantographs, because even if pantographs are used today by the railways widely, it's a slightly different kind of pantograph, plus there's only the adaptation to fit it on the truck. So the expectation is that the cost of the pantograph itself, so the cost attached to the trucks, will go down as the technology becomes more widely adopted with economies of scale. And this is what we have included in our simulator. We start with a cost of 70,000 today, going progressively down to 20,000 in 2040. And this cost reduction comes from the literature. I think we have one source from the International Energy Agency, and you will find all the source in the report. The cost of the catenary, on the other hand, so building the overhead lines and the substations, we do not consider cost reduction, because this technology is fairly mature today. I mean, there are thousands of kilometers of catenaries built for railways, and it's not that different from what is done for railways. So we do not consider that the cost of the catenary system itself will go down, and we have a fixed cost per kilometer in our model.
Thank you. So somebody asked, could the e-highway work for container trucks that are quite high? Clara, I don't know if you...
I don't really have a specific answer to that. When discussing with Patrick Eckermann from Siemens, we asked him whether some trucks would not be suitable for the technology, and it appears that the technology is quite flexible, so could be used for a wide range of trucks, so not limited to one specific kind of trucks. This being said, as Joanne was mentioning, the best is probably to reach out to him if you want a specific answer to that question.
Then we just have three, I think, questions left. Can we think that a good train system can be better to transport huge quantity of products at a better price? Well, I would say yes, but I will let Clara
Well, I don't really have an answer in isolation. I mean, rail is definitely a good option, but it's been there for almost 200 years, and it's not that widely adopted today for reasons. And obviously it's less flexible. It's more complicated for last mile logistics, because you have to transfer from the train to another mode of transportation. So I think what's interesting with e-highway, again, is its flexibility, because it's as flexible as the trucks that we have today. When railways comes with many constraints, and is more complex to deploy. This being said, we would really e-highway with other technologies, and taking into account intermodality, the possibility to transfer some of the long distance freights to trains, not only trucks.
So just a last question, somebody asked, would such study share more light on the adaptability of the technology to our climate? And then could this be combined with Hyperloop infrastructure? I think that, I mean, anything's possible. Hyperloop is still much more, I think, far out than perhaps other options. I mean, it's perhaps beyond the scope of what we were considering. But I mean, in terms of adaptability, I think that's the whole point. We want to see how flexible it can be compared to other options which are currently being considered. Clara, maybe you have something to add?
No, in terms of how would the e-highway technology work in our climate? We already said everything that we have. Yeah. Unfortunately, to go further than that, we would need to have detailed feedback from the pilots in Northern Europe to see what kind of harsh meteorological events they had to withstand and how it worked, and also some calculations. I mean, it can all be done by engineers. We are not at the stage where we are doing a detailed engineering study of the technology, so no, we don't have more answers for now, unfortunately.
Great. So, well, thank you everyone for joining us. If you have questions or any form of comments or recommendations of studies that we may not have had the chance to look in our study, please do contact us, send it to us, and so we can consider it hopefully in our broader study, and hopefully you will have had an enriched experience. We had fun doing this, and hopefully it can help us advance for decarbonizing freight. Thank you. Have a good day.